Our star. The sun. The source of our light, all our heat, all our energy.
The sun is really the power source for the entire solar system. So without the sun, life on Earth would probably be impossible. The energy that we receive from the sun is crucial for a start keeping us warm, for providing energy for the plants to grow. It drives our weather. The Earth would be a completely different place if it wasn't for the sun.
Yet close up, our star presents us with a far more violent picture.
The temperatures are so high at the surface of the sun, humans wouldn't be able to survive. And along with that, the sun doesn't actually have a solid surface. The density is more like that of water, so you wouldn't be able to stand on the surface. You would start to sink in to this very hot, highly charged gas.
We've both worshipped and feared it for thousands of years, but only recently have solar astronomers truly begun to understand our local star.
To really get the best view of the sun, you need to go into space.
We've now put an array of telescopes into space and pointed them at the sun.
I can tell the spacecraft, or in particular my instrument, what to do from anywhere around the world. All I need is an internet connection and a laptop.
Different instruments allow astronomers to look at the sun in different ways.
Today we have instruments which are able to see the visible light coming from the sun. We can see ultraviolet light, extreme ultraviolet light, X-rays, and it is crucial that we have this complete coverage.
Solar astronomers are revealing the secrets of our star.
The sun isn't a perfect and unchanging object. It actually has sunspots on the surface, and from the Earth they look like black features on the surface of the sun.
Sunspots are areas of intense magnetic fields that effectively create a cold spot on the sun.
If you were to be able to cut out a sunspot though and put it in the sky, it would have the same brightness as the full moon. It's just that relative to the surrounding surface they appear dark.
It is around these sunspots that our solar telescopes have revealed even more dramatic events. Solar flares.
You can see that they have loop-like structures, and that's because they're associated to the very strong magnetic fields in the sun's atmosphere. Solar flares are immense, so this one running here would span an area many times the size of the Earth.
Perhaps even more spectacular are a phenomenon known as coronal mass ejections.
They carry about the same mass as Mount Everest into the solar system at speeds of millions of kilometres an hour. The very big eruptions go possibly to the edge of the solar system. What we're looking at here is a fantastic movie which has been made by the Stereo mission. The movie shows us the sun in the bottom left corner here, but if you look, you'll see that there are these white clouds of material that are moving out into the solar system, and these are coronal mass ejections. And the scale I have here is that this material moves all the way over to the Earth on the right-hand side. Using movies like this from the Stereo mission mean we can track coronal mass ejections and the potentially hazardous effects all the way out to the Earth. The way that the sun is viewed today is that it has an outer atmosphere which extends over 10 billion kilometres.
Blocking the sun with a disk shows us more clearly how the sun's atmosphere extends out into space.
We really shouldn't view the sun and the Earth as being unconnected objects. They are connected through the fact that the Earth is sitting in the sun's atmosphere, and anything that happens in the sun's atmosphere affects us here on the Earth.
We call this space weather, and its effect on the Earth depends on where the sun lies in an 11-year activity cycle. This speeded up movie shows how the sun passes from quiet to violent periods of activity.
Now, interestingly, for the last 2 or 3 years, the sun has been at the minimum of the activity cycle. But we are coming out of that minimum now, and the activity will start to ramp up. And we're not sure what the size of the next peak will be, but we certainly do need to follow what the sun is doing so we can try and reduce the effects that this activity has on Earth. And that will include effects on our aircraft, on our satellite systems, on our communications. It could be that the satellite that your mobile phone is using fails, and also our electricity networks as well. The sun is really an object that we need for our day-to-day lives, but it is also an object that can destroy aspects of our day-to-day lives. So we kind of love and fear it in equal measures, maybe. And really, we should be respecting the sun, and in particular, we should be studying it to understand what it's doing.
Well, way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out. And at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is that the outer layers of the star get farther and farther from the middle. The force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead, remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang! The outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star, billions of years ago before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
Here's a simple demonstration to show that there's more to light than meets the eye. If you point the front of a remote control at a digital camera or a camera phone and press the buttons on the remote, then on the screen of the camera you can see the remote's LEDs light up. Domestic remote controls use near-infrared light to send signals to equipment. The wavelength of near-infrared is very close to visible light. It's slightly longer than red light, and the sensors in digital cameras are responsive to those frequencies, even though our eyes are not. Using a 12-volt bulb, a power supply and a variable resistor, you can demonstrate the different colours of stars as they glow at different temperatures. Start with the bulb glowing dimly. You'll notice that the filament is glowing faintly but red in colour. Use the resistor to increase the voltage across the bulb. As you increase the voltage, the brightness and temperature increase, and the colour changes to orange and then to yellow. At full brightness, the filament is glowing white hot. This demonstrates how we can use the colour of a star to tell us something about its temperature. Red stars are relatively cool, white stars are hotter. The Hertzsprung-Russell diagram plots the star's brightness and luminosity against its temperature and stellar class, illustrating the characteristics of different types of stars.
Temperature 2500 Kelvin, luminosity 10 cubed.
Get your students to create a large Hertzsprung-Russell diagram. You can then do several activities of varying demand using the diagram. In this case, 10 cards each had a pair of values for a single Sun-like star during its evolution. One value either about spectral class or temperature, the other value either about absolute magnitude or luminosity. Note that on the Hertzsprung-Russell diagram, the star's temperature increases from right to left.
Temperature 3200 Kelvin, luminosity 10 squared.
One student reads out the fact cards, whilst another takes small steps to trace the changes in the star's characteristics throughout its life.
Temperature 3000 Kelvin, luminosity 10 to the power 4.
The task could be further extended by mixing the card sequence beforehand for the students to correctly sequence themselves as a group activity.